So here we will be looking into the machine learning models or algorithms. What we have seen so far is on ML performance metrics, such as confusion matrix, sensitivity, specificity, receiver operating characteristics, and area under the curve. They allow us to know how good the ML model was, but we didn't get into any specific details about the model that we used. So in this session, we will look into some popular ML models and the associated techniques, the mathematical approaches that are relevant to those techniques. Broadly, the ML models could be grouped into three categories: supervised machine learning, unsupervised machine learning, and reinforcement machine learning. As the name indicates, in the supervised machine learning, we have the data which are labeled. Typically in the medical domain, the labeling is provided by the experts who are familiar with the disease. So they label the data to have a normal characteristics or abnormal or diseased characteristics. So label the data leads us in designing supervised machine learning techniques. In an unsupervised approach, we do not have labeled data, so we figure out how the grouping is done algorithmically. So here there is no labeled information being provided, or it's not available. Whereas reinforcement learning is a concept where there's a feedback involved in the learning mechanism, and the feedback helps the model to become better as it goes by. So in reinforcement learning, there's a feedback associated with it. In general, people stick to supervised and unsupervised learning, and it's very obvious that in supervised learning, because of the labeling, we do need domain experts, or we could have a ground truth from the domain experts, and that allows us to compare the performance of our machine learning with regards to the labeled data being provided. And specifically, in terms of individual techniques, we have seen quite a few techniques with very high-level examples, which need not be in medical domain. For example, we looked into spam filtering, looked into making decision about university college admissions, looked into techniques which could allow us to locate shops for pizza, for example. So that particular thing covered general machine learning frameworks. And in this lecture, we will look specifically in how we could bring it to the context of biomedical signal classification. So specifically, there are many methods. The most popular ones are linear regression, you have logistic regression, you have LDA or linear discriminant analysis, then you have naive-Bayes classifier, you have DT or decision trees, you have SVM or support vector machines, you have ANN or artificial neural networks / deep learning, and finally you have clustering techniques. So these are kind of the popular schemes that have been implemented in many biomedical signal classification applications. Each one has very strong basis and theory attached to that. And in many cases, we can find the connections between the techniques as well. So they're also to some extent interrelated. Techniques are based on optimization problems, and they also depend quite a bit on linear algebra, specifically looking into matrix operations. So in terms of basic mathematics that's needed, it's understood that you have fairly good background in linear algebra, especially with matrix computations, and also in doing some optimization, specifically least squares optimization. So we will get into the details of few of the techniques in today's session. Specifically, we'll look into 3 techniques. And the first one I would like to cover is on a logistic regression. Logistic regression is a very simple supervised machine learning technique, which is based on a curve called the sigmoid curve. This curve is also called as logit curve, logit, L-O-G-I-T, logit curve. And it's mathematically given as f of z. Okay, so this f of z function is nothing but e to the power of z divided by e to the power of z plus 1, which could also be written as 1 divided by 1 plus e to the power of z. Now, the key aspect is in designing a z variable, which is nothing but z is defined as a weighted combination of b's and f's. Okay, so z equal to b0 plus b1 f1 plus b2 f2 plus so forth bp fp. Now, what are these variables? B's are called the logistic regression coefficients. In other words, it could be seen as a weighting function. And F's are your feature vector. So you have P of those feature vectors. So here you see we are not feeding the signal directly into the classifier. We are feeding the features. And we assume that you have gone through a good feature extraction and you have extracted P of those features. Okay, so these features are getting weighted. That's as simple as that. Probably a feature which is very dominant, it will get more weighting and so forth. So this is not done manually, it's done automatically. Okay. So you would have come across that certain features might be doing a good job in your classification and you might give a higher weight to that. But in this thing, the weighting is done automatically. So the weights for these features B0 up to BP are done through a mathematical concept. So the idea of estimating B's is simply based on 2 popular method, method of least squares or by using maximum likelihood estimation, which is more like trying out different values to see which one gives an optimal value. Okay, so method of least squares and MLE we will expand when we come into the adaptive filtering topic. But those are the 2 ways where the coefficients B's would be optimized or estimated. So once you have this optimal coefficient Z, then it's a matter of putting that into that expression of Z, and then you get the f of Z function. When you plot f of Z function, it gives the sigmoid curve, which looks like this. And the good thing about this curve is that no matter what, the curve takes a value between 0 to 1. Okay, now it's up to you to draw the threshold to tell which group it will belong to, depending on what accuracy you are experiencing in training. So let's assume you decide 0.5 as a threshold. So essentially through this process, we say if your function f of z for a new sample, which typically comes in the testing phase, has a value of above 0.5, then it belongs to, let's say, class A, just as an example. If it's below 0.5, it belongs to class B. Okay. So it's a simple threshold-based classification once we know f of z, and that's given by the sigmoid curve, which takes a normalized range of 0 to 1. So as the name indicates, it is a 2-group classification, class A, class B, because this particular curve takes continuous values, and that's what's typically called a regression. A regression is something that takes continuous values. You can convert a regression into a classification problem by applying suitable thresholds. And in this case, we have applied a threshold of 0.5, and we say anything above 0.5 is class C and class B, and we can run through the ML performance metrics. So what you're getting with this particular threshold is actually 1 point in the ROC curve. Okay, if I change my threshold to different values, then I can get many points and I can plot an ROC curve. And that's exactly we saw in the previous lecture on how to get receiver operating characteristics, okay? Because each threshold will give different sensitivity and specificity, which also impacts the true positive rate and the false positive rate. And that also has an implication on the classification accuracy, okay? So that's in a nutshell, the simple logistic regression analysis, and it's very commonly used in many biomedical classification problems, especially if you just need to classify two groups, for example, normal, abnormal group classification. You got to keep in mind these techniques were developed before we had a lot of computational power. Okay, so an approach like logistic regression is very suitable when you have low computational resources. Let's say you want to run your AI or ML technique on a smartphone or a device which is not as comprehensive as a computer with the GPUs, then logistic regression comes in very handy. And in many approaches, especially with small data set, it gives a very efficient and optimal results that one could expect. We will look into a little bit more detail about a second popular technique called LDA, or linear discriminant analysis. LDA, as the name indicates, it does some form of a discriminatory output, like it will be able to help us with classification. So here, let's assume we have a feature vector, but I will be using X as my feature vector. And it's again P features. Okay, so we have assume P features of X. Now, the idea is that let's assume there are N1 samples, or in this case, in biomedical signals, we call N1 signals, okay, coming from maybe from N1 subjects, okay. So that's kind of belonging to class W1, and N2, that the number of samples in the second class W2. So the whole idea is that we want to find a scalar y, where the y is given nothing as the projection of the samples X onto a line, okay? Projection of the samples X onto a line. Here the line is W, okay? So that's written as a WT transpose and X. So this is a notation for getting that scalar. Now we could also go and for each of the two classes, in this case, class 1 and class 2, W1 and W2, we can compute the mean, and the mean is given by mu I, or in this case, mu1 and mu2, which is basically adding the samples X1, X2, X3 like that, and dividing by the number of samples for each class, you get the mu for each class. And while computing the mu for each class, we could also do that substitution, and basically now the mu I for each class is given by this notation, okay, this notation. Now the idea is to find out the distance between the two means, okay. So in LDA, the principle is to make these two means as far apart as possible. Okay, separate the means as much as possible, and that's what it's been done in the next step, is by basically trying to separate the mean by taking the difference. Okay, so that has become the objective function. The objective function in machine learning things, we tend to use the word objective function or the loss function interchangeably. It means mathematically we are working on those objective or loss function, and we are applying an optimization technique to make it smaller or efficient. Okay, so here the objective function tends to be j of w, which is nothing but it's basically the difference of the two means. And you could see this particular metric here will not be a good measure by itself, because yes, we have taken the mean and we are trying to make it as apart as possible, But when we're trying to make it as far as possible, the dispersion within each class, like the class W1 and the class W2, will have a scatter. The samples will be scattered. The dispersion of that would be uh, present, and there is no information about the dispersion of that. To give an idea, let me just draw with two possible cases. Okay, so let's assume I have class 1, which is all red points, and let's assume we have a class 2 W2 with the blue points. Okay, and there are also some blue points which are overlapping here. Okay, so the idea is to see, let's assume this has a distribution for the blue, and the red has a distribution like that. So each one has a mean, and they also have a, so these are the mean. Okay, so this could be mu2, and the red one would be mu1. So these are, so the idea is to keep this distance as far as possible. Okay, is to basically, this green line should be as far as possible so the two classes get separated. But while the two classes are getting separated, we also have to keep in mind the dispersion factor or the standard deviation. Okay, so this is this value here, this value there. We need to make sure that's also factored in this expression there. So in this expression, all that's factored is mu1 and mu2, but we need to include somehow that standard deviation information. So in this particular LDA, that standard deviation matrix, or which is also related to variance, because square of standard deviation variance is known as the scatter variable. So the scatter variable is how much you deviate from the mean for each class. So this is defined for each class. In this particular example, we have two group. So we will have S1 and S2. Okay. So this S1 and S2, the scatter matrix, is that standard deviation. S1 is a standard deviation, for example, of this red plot. We can call this as S1, and we can call this S2. So S1 and S2 are what's called the within class scatter. Okay, how much is the deviation between the class 1 and what's the deviation within class 2, or S1 and S2? Okay, so they are called the within class scatter. And the within class scatter, the formula that we just worked out, if we go back and we substitute the values, then it turns out the within class scatter matrix could be written in terms of W function. W are again the weight functions, okay? Weight functions that we defined in the beginning of the LDA description. Now, once we have the projections of the means onto that LDA line, then we could also have what's called the between class variance or between class scatter. Okay, so the between class scatter is basically when we go through this expression of mu1 minus mu to the whole square, basically it's saying how much is the difference between the classes. Now that leads to an expression which is like that. So if you see here, there are two matrices in the example we just covered. We had a scatter matrix SW, which is nothing but how much is the variance happening within a given class, and SB is the scatter matrix for between the class. So what is the variance between the two classes? So to give an idea, if I go back to the diagram which we had, so in this particular diagram, so this is, if you take the variance here, this is a within class variance. And when we take the variance of this particular distribution, then it's called the between class, okay? Between class variance. So two simple parameters are calculated again. Here is nothing but means of the classes and the variance of the classes. The only difference here is that we call the variances as scatter, because that's the terminology that's used in LDA technique. So once we do that computation, now all we have to see is that there's a fission criteria which basically says the J of W. We try to optimize. This is becoming a function of the weight vector W. Has become this expression, which is nothing but in the numerator you have the between class scatter matrix involved, and whereas the denominator you have the within class scatter matrix involved. So the idea is to maximize your function J. So maximizing J is an optimization problem which says I'm going to be maximizing the between class scatter, okay? So between the two classes scatter, and I might be minimizing the within class, okay? So to put it in other ways, we try to decrease the what's called in simple language as intra-class variability. We tend to decrease the intra-class within group variability. You try to decrease. And on the other hand, we try to increase the inter-class, in other words, between class variability. Okay, we increase that. So as we increase that, which is again in the numerator, and intra-class variability, which is a scatter matrix within class, is decreased, then the overall function increases. Okay, so that whole idea is to maximize this J. So it's obvious, like for example, if we are assuming the problem of heart rate, we have heart rate varying even within our own physiological process, and the idea is to try to minimize within our own variation so that we don't end up crossing into another category, which could be an abnormal heart rate. Okay, so your heart rate, for example, could vary between 80 to 110, and if you assume that anything above 120 is considered to be abnormal, you may need to decrease that intra-class variability, which is 80 to 110. That's intra-class variability. You need to decrease it to make me bring it 80 to 90. This way, you're very confident that this intra-class variability is not going to enter the next group. Okay, so that's basically the whole idea of linear discriminant analysis. Is basically it's increasing the inter-class variability, or in other words, between class scatter matrix, and decreasing the intra-class variability or decreasing the within class scatter matrix. Now scatter is nothing but the variance of that particular sample distribution. In this case, it happens to be the feature distribution. So that's essentially LDA, and LDA is a very powerful technique. It's based on supervised learning, obviously, because we have to determine the within class labels, and it comes from ground truth information. So it's a very popularly used supervised machine learning approach. LDA is very much similar to the concept of principal component analysis called PCA. Okay, PCA is a statistical concept, whereas in LDA, it's more like a machine learning concept. But they are all interrelated. The underlying mathematics is quite similar, but in LDA, intentionally, we have modified it to behave good for a classification application. Okay, both LDA and PCA does a dimension reduction, so there are a lot of parallelism to that. So if somebody is familiar with PCA, you will find the math that we just discussed is similar to what you see in principal component analysis. So the next technique I would like to touch upon, the third technique today, is on K-means clustering. K-means clustering, by the name indicates, is a clustering approach, and any clustering technique tends to be unsupervised technique. And K-means is one of the simplest unsupervised technique. And it basically involves 4 key steps. Okay. So here, because unsupervised, the assumption is we do not have labeled data. So it's an unlabeled classification problem. So here, it starts with defining what's called centroids. And centroids are nothing but a geometrical means. Okay, they're nothing but geometrical means. Okay, so you would plot the features in a scatter plot. Okay, so you will have the features. Let me just take an example here. Okay, so let's assume some red guys. Okay. And just for convenience, though we don't know the labeled information, like we don't know which is red and blue to start with, just putting for explanation convenience. Okay, so this is basically in the x and the y axis we have two features. Okay, let's call feature 1 and feature 2. Okay, so the idea here is that using these features we will define k centroids. Okay, so centroids are geometrical mean. So randomly, let's assume we start with 3 centroids or 3 geometrical means here. So I would take one here, another one here, another one there. Okay. Okay, so there are 3 green points which could act like 3 centroids, and typically we have a k of those centroids. Okay. Now we would assign these features, blue and the red guy, to the closest centroid they are. So we will take a distance matrix. It's nothing but a norm, a vector distance between this centroid and the available features. So for example, it's obvious these blue guys, they all will be classified into the first centroid. Okay, they are closest to that centroid. Whereas here in this particular second centroid, we have the points which are closest to the second centroid. They all will be classified as group 2. So this is, let's call group 1. This is group 2, and there's another one, group 3. Okay, so we would basically assign each vector to the group that has the closest centroid. Okay, so that's the second step. When we have assigned all the feature vectors, then we will recalculate the position of the k centroids, because you will have 3 clusters. For example, we have 3 clusters. Then we will start to recompute the center, the geometrical means of that, and these are called the centroids, and the k centroids gets recalculated. We would repeat the steps, both 2 and 3, until we find the clusters don't move anymore. That means you've reached a steady state, and basically the features have now found a closest centroid, and there is no ambiguity. So this is a very simple technique. Okay, so essentially you start with k centroids, then you assign each feature vector to the closest centroid by taking the distance matrix. It's nothing but the length of the vector. Okay, so you just take the vector length, then you assign it to that particular centroid. Once it's done, then essentially what happens is that you recalculate the geometrical mean again, and this time the clusters are the centroids are moved. Now you will get newer k centroids. Then you would repeat this process until you find the centroids are not moving anymore. Okay, so the whole process could be seen as optimizing this objective function. Again, it's an optimization problem. Some people call loss function. We will be minimizing this objective function. We'll be minimizing j here. By minimizing j means, so if this is your feature vector and this is your centroid, this is centroid, and f is your feature, then this is a distance that we are taking. We're trying to minimize that distance so that it will belong to one of the j's, and basically the j is the number of clusters k. Okay, so that's why it's called k means algorithm, because means is nothing but we are taking the geometrical mean, so we have k of those, so it's called k means technique. And the feature, just like how we decided before, we are not sending the signal anymore directly to the classifier, we are only sending the features. So the feature is assumed to have p vector length p, or it's a 1 by p feature vector. Okay, so this is how we do the k means. It's just it might be quite time consuming if you a lot of features and a lot of clusters. Simple reason is that we have to keep computing this distance metric for each of those points, okay, for each of those feature vectors, distance metrics. Okay. Otherwise, here we don't have to worry about labeling. There's no need to tell is the feature belonging to group 1 or group 2. You can send the features as it is, and you see how the clustering turns out to be. It's also used in many applications to start to label a signal. Okay, so let's assume we don't have the domain experts to label the signal, and you wanted to get a high-level understanding of how the features are nicely clustering, which might help with the subsequent labeling, which could be used to send to a second level of supervised learning. Then this kind of a approach comes in very, very handy. There are a lot of modifications of K-means clustering, because Kmeans is one of the simplest one, but there are a lot of modifications of that, and it's getting quite popular because labeling is very time consuming, especially with big data applications. So people are relying on computers to help with some kind of clustering, so the labeling could be taken from there. There is also another technique called K nearest neighbor technique. So the word might be confusing a little bit. K means is that we are taking means and centroids. K nearest neighbor is that essentially it's a supervised approach. KNN approach is supervised approach. Basically, an unknown feature is looking into its K nearest neighbor in terms of distances, and it will find out of those K nearest neighbors, majority of them, which class it belongs to. And that particular unknown feature would be classified into the neighbors which are most dominant. Okay. So it's a simple supervised learning approach. So just wanted to point out there is a subtle difference between K-means and KNN in terms of the way it's been described, but it's a supervised approach, KNN, whereas K-means is an unsupervised approach. So we will stop into looking at the descriptions of these techniques for now. Towards the end of the course, we will come back again and revisit a couple of advanced techniques like support vector machines and neural networks. Because for those techniques, we need to get into a little bit of details about some of the optimization algorithms, which I will cover next. Thank you.